Before we start notes, so far I know I can't make another quiz today. I'm still going to try tomorrow, but if I can't get it up by tomorrow, get a quiz number 3 on Canvas tomorrow. Then we're just going to have 2 quizzes this semester as part of your grade, each worth 2%. But if we can have 3 quizzes, then we'll have 3 quizzes, each worth 2%. So for now, we're going to finish notes for chapter 4. I want to start chapter 5, but there's really no rush. Just as long as we continue to push through the book. Yay. Okay, so we're just doing one more problem. I'm going to rewrite the problem, and I've broken it up into a few parts. So a rock is thrown off a cliff. Oh, it's 350 feet high. Tall. And it's with an initial velocity of 10 feet per second. So part A, find the position function. Part B, when does the rock hit the ground? And then part C, what is that impact velocity? Oh, no. Okay, we're using just use a sock. Cool. And that's all we're doing for part A. So even though your problem doesn't tell you anything about gravity, we are, near the surface of the Earth, and we do have gravity. We're going to use units of feet. So it's negative 32 feet per second squared. So there's a lot of different notations to use, but I'm going to try to make it clear and stick with my notes. So we have first our initial conditions, and then some antiderivatives. Thrown off a cliff. Let's draw a picture as well. We had a picture last time. So our variable is going to be t for time. And our person is over here at the top of the cliff. Okay, and then they throw a rock with initial velocity. So it's just going to go, they don't just drop it, because if you drop it, that's velocity, initial velocity as 0. But the initial velocity is 10, so they're going to toss it upwards a little bit. and it's going to hit the ground. All right, let's put that label as how high we are. Here to here is 350. Cool. And let's put our initial velocity. Actually, first let's start with some like initial conditions. I like to start with time. And then we can talk about position, initial position, being at this position at time 0. And then initial velocity is that kind of upwards. Okay, for this problem, the initial time is at t equals 0. The initial position is s of 0, which is 350. Let's go from here to here. S of 0 is equal to 350. Okay, and then the initial velocity is v of 0, which was 10. So velocity at time 0 is 10 feet per second. That's all the information we have. We're going to use the acceleration function, get an antiderivative, and that gives us the velocity function. So I call this part A. So part A, get an antiderivative, which is a general solution. We'll have b of t as the antiderivative, and it will be negative 32t plus some constant we're going to call c sub 1. So plus some number. Part B, use one of your initial conditions to find that number. So far I know something about velocity, so we're going to use this part. The initial velocity is 10, so put in t equals 0 to that function. B of 0 is negative 32 times 0. Add c sub 1. Okay, so 0 right there. V of 0, we can substitute that number 10 in place of V of 0. So on this side, we're putting a 10 right here. On this side, we just simplify. Yes. Okay, I got 10 as C sub 1. v of t is negative 32t plus 10. So we're going to repeat these steps. We're going to get an antiderivative and use initial conditions, but this time to the function for velocity. So going from the velocity function to the position function, get an antiderivative and then use initial conditions. Okay, the antiderivative of v of t will be s of t. Of v of t, which remember is s prime of t, will be s of t. Okay, and we're going to figure that out. So you have your constant. The antiderivative of t is t squared over 2. The antiderivative of 10 is 10t. Okay, and then you have to add some number c sub 2. Okay, so part of the initial conditions will help you solve for that number. How to use that info. Cool. So we want to use the part where it said s of 0 was at 350. So put in t equals 0 to the function that you found, or that we found. Negative 16 times 0 squared. Add 10 times 0, add c sub 2. So on this side, we'll simplify what's going on. Over here, this number is equal to 350. Okay. 0 times anything is 0. Add 0. Add c sub 2. Okay, 350 is equal to c sub 2. So we have the full position function with s of t, and we'll simplify. S of t equals negative 16t squared. Add 10t, add 350. Okay, we're on to part B. So when does the rock hit the ground? Okay, so let's see. From the picture, trying to think. We want the height to not be like 1 or 2 feet at 0 feet. That's when the rock has reached the ground. We'll say when its position is at 0 feet. Okay, which means we want S of t equal to 0. Okay, so just to not lose any info, we have your function, which you can restate, and then on this side, we're putting 0. Okay, so we use the what's it called? Quadratic formula. Cool, t is negative b, negative 10, plus or minus the square root of b squared minus 4 times a times c. Okay, divide it all by 2a. So you get two numbers, one where you add that root and one where you subtract the root. So the first value I got was t equals negative 4.375. T equals 5. T represents time, so we're not going to use the negative time, we're going to use this t equals 5. I think seconds. Yep, 5 seconds. Okay, right. Last part. What is the impact velocity? So the velocity at the time when the rock hits the ground at the time of impact. So we want to use the previous problem and take that time, put it into the function we have for velocity, which was in our scratch work. So our velocity function looked like this. V of t was negative 32t plus 10. Okay, so find v of 5, which is negative 32 multiplied by 5, add 10. I got negative 150 feet per second. Cool. And that's the end of chapter 4, but not the end of notes. I think we have some time. We're going to start chapter 5. So at the beginning of the semester, I talked about how Calc 1 focuses on derivatives, tangent lines to curves. Calc 2, the main focus is area under curves, which we're going to work on for the rest of the semester. I know that when I did Calc 2, my teacher started us, I think, in 5.3, but your teacher might start at the end of chapter 5, which is why I want to make sure we cover those sections, if we can. Cool. Okay, so first of all, we have a function. We're going to call our function f. And all we really need is for it to be a continuous function. But for chapter 5.1, we're going to talk about functions that are above the x-axis. It needs to be continuous. I'm also going to pick functions that are positive. On AB. Closed. If f is a continuous function and positive on AB, then we're going to fully explain what's happening. So it's the area under the curve to the x-axis. from x equals a to x equals b. Is, okay, I think I'm going to go ahead and use capital A for area. So our area is approximately the sum of a bunch of rectangles. So this is how we're going to write it, and then of course a picture will help. Okay, again, we're going to approximate the area by taking a width called delta x, multiply by some height we're going to call f of x sub I star. Actually, let's do a few of these first. We're going to have x sub 1 add delta x times f of x sub 2. So this is the width of a rectangle and its height, plus another rectangle with the width times height. We keep adding. All of your rectangles together. So this expression here would be the sum from I equals 1 to, we would end at delta x times f of x sub n. So we're going to go to n. F of x sub I, and this is where we want to put a star as a superscript, n times the width delta x. So first we'll have a picture. Our function is called f. We're going to go from here, swoop to there. It's continuous, and it's above the x-axis. We start at A, and we go to B. We're going to talk about how we split up the interval between A and B into subintervals. Each of those widths is delta x. So here to here, delta x. So here to here. All right. There are three ways that we are going to make rectangles. So one way is using the left hand of each of the subintervals. So for the picture, between here and here, choose the left side, go straight up to the function, and use that as the height of a rectangle. Okay. On this interval, we're going to choose the left side, go up to the function, and this is the height of your rectangle. Okay, again, starting on this side, touch the function, create a rectangle with that height and width delta x. This side reaches the function, goes over, makes the rectangle, go up to your function, over. So this rectangle is a little short of your function, which is why we're going to put it's an approximate area. Because we're going to add this rectangle's area to this one, to this one, and that one, and that one. Which is missing just a tiny bit of area, but it's mostly going to represent the area that's under the curve and touching the x and reaching the x-axis. All right, so talking about different ways to make these rectangles. Oh, also talking about delta x. Delta x is b minus a divided by n. We want to break the interval into n subintervals. Okay. For the homework, you'll be told like what choice to use for n. If you want n equals 3, 3 rectangles, n equals 10, 10 rectangles, and such like that. Okay, then build the rectangles. Number 2. So we've talked about the width of the rectangle. We want to talk about the height. So for the height of the rectangle, there are 3 choices. There's right hand, left hand, and midpoint. So for the right hand endpoint, we're going to use the notation capital R sub n, which we'll use most often. Okay, but you could use left hand endpoints, which are going to be L sub n. And if you take your interval and find the midpoint, then we're going to call that M sub n. And just remember that a midpoint is the average of the 2 endpoints. So I'll write down all of that. Okay, so you can use the middle midpoint. M sub n. So some of these problems are going to be easy to sketch, and then we can just draw, like use the drawing to find either midpoints or the left-hand points or the right-hand points. But if you really can't draw what's going on, then we need to talk about the intervals. So if you go from an interval that contains x sub I minus 1 and goes over to x sub I and includes that endpoint with a square bracket. This is called the ith interval. And I'm just going to put where we want I to go from 1 to n. Okay, so I feel like I'm going to do one example, like the first interval is when I is equal to 1, that very first value it can be, and you would put in x sub 1 minus 1, x sub 0, and go over to x sub 1. And the very last interval would look like this. Where you put in the last value, I can equal n. X sub n minus 1, go over to x sub n and close. The drawing helps. So before we keep going, I've kind of gone on a tangent, but it's okay. We have a number line for x. We start at A and go to B. And then we create subintervals of width delta x. The very first interval goes from x0 to x1. And then the next one goes x1 to x2. This picture would go from x2 to x3. And B would equal x sub 4, which means in this case, I went from 1 to 4. Oh, that's not looking good. The reason I'm doing this is to talk about the midpoint of an interval. Okay, so like the middle of this interval is the average of the two values. So you take this side, add it to this side, divide by 2. You take x sub I minus 1, add with x sub I divided by 2. Okay, let's do a problem. So we're going to try the function f of x equals x cubed. our interval goes from 0 to 1. And I'm going to use n equals 2. And for practice, we will do right hand, left hand, and midpoint. Start with finding delta x. We're going to need that for all different heights of the rectangles. Okay, a subtract a, divide by n. This is a, and this is b. So I need 1, subtract 0, divide by 2. I got delta x equals 1/2. So first one we're going to do is right hand endpoints. We'll sketch this function from 0 to 1. X cubed kind of goes through the origin and then swoops up. Okay, our two subintervals have a width of 1/2. So 0 over to 1/2, and 1/2 to 1. We're going to use right hand endpoints. For the first interval, choose 1/2. For the next interval, choose 1. So we'll go to 1/2, find f of 1/2, and use that as the height of the function to make a rectangle. In a minute, we will find f of 1. F of 1 is the height of the rectangle. And then we'll add the two rectangles together. This one with this one. Okay, every time we take the width times the height. So the width is delta x, the width of 1/2. Times f, and in this case we chose f of 1/2. Add the area of that rectangle, 1/2 by f of 1. Okay, area is approximately this number, when this number would be 1/2 times 1/2 cubed plus 1/2 times 1 cubed. So just put that into your function and then put 1 through the function. So I actually don't have all the work for this one, but we'll grab a calculator. This would be 1 over 2 to the 4th, or 1 over 16. That's 1/2. or 8 over 16. So I've got 9 over 16. Just double checking. My notes say that the actual area is less than 9 over 16. That's because you can kind of tell that these rectangles are going to have more area than the area that's under the curve. Using A for area, the area under the curve, it would be less than that number. Okay, next one will be the left-hand endpoints. It's the same function, and we're on the same interval, but new rectangles. We go from 0 to 1. And we're trying to find the area under the curve. So just, by the way, what we're looking for is this piece right here. That area. We're going to approximate it with some rectangles. So our delta x is still 1/2. Go from 0 to 1/2, and 1/2 to 1. For the left-hand endpoints, our first rectangle has height of f of 0, and the other rectangle has height of f of 1/2. So this one, f of 0 is 0, so it's a height of 0, and just over, so it's like an area of nothing. And this one has a height of f of 1/2, which hits the curve right here. And then you go over and make a rectangle. So this area is definitely going to be less than what the area under the curve is. So we're only going to get this little rectangle here. Okay, this time, area is approximately the sum of the two rectangles, which this is like an invisible rectangle. So it has a height of 0. We take width 1/2 times height f of 0. Add the other rectangle, width 1/2, height f of 1/2. And that would be 1/2 times 0. Add 1/2 times 1/2 cubed. So 0 plus 1 over 2 to the 4th, which was 1 over 16. Okay. And then a little note on the side. This area under the curve, we're going to call A, is greater than the area of the rectangles. So let's talk about using midpoints. And 7. still have the same function, which might kind of leave here a little bit. So we're looking at f of x equals x cubed. Our interval goes from 0 to 1. We make two subintervals. Each has width 1/2. And this time we're going to use the midpoint. So with this drawing, I can find the midpoint. Halfway between 0 and 1/2 is 1/4. This is 1/4. Add another 1/4 is 2/4. And then the next one is 3/4 till you get to 4/4. But we can also use that formula that I wrote earlier. Okay, so the first midpoint is to take the subinterval, add the ends, and divide by 2. So take 0 plus 1/2 over 2, which is 1/2. Multiply by the reciprocal of 2 over 1, so times 1/2. There, 1/4. Check. Cool. Let's check this one out. So my other interval went from 1/2 to 1, and the midpoint is to take 1/2, add it to 1, divide by 2. So it's this part that we want the midpoint of. We take the ends, add them together, divide everything by 2. So 1/2 plus 2 over 2 is 3 over 2. And then take that number, multiply by 1/2. Same trick as I did right here. I've got 3/4. Sweet. So I'm going to the midpoint, find f of the midpoint, which means you go up to your function, and go left and right to make your rectangle on that first subinterval. Okay, next midpoint, go up to the function. From that point, go to the left and right to create the top of your rectangle. And come down on this side and down on that side. Okay, then we'll take this area, add to this area. And that's approximately the area of the curve. That's the area that's under the curve and to the x-axis. So when you do it this way, your area is about delta x, which was 1/2, times f of the midpoint, f of 1/4. Add the width of 1/2 times the height of f of 3/4. Okay, 1/2 times 1/4 cubed. Add 1/2 multiplied by 3/4 cubed. And I have done this one before. I got 7/32. Okay, I have one more note about this, and then let's see. We will try to do just a bit more, but then pick it up again next time or tomorrow. Okay, so the last thing was from the work we did earlier. We know that the area is somewhere between 1/16 and 9/16. 1/16 was that left hand part, and then when we did the right hand part, it was much greater. And let's see. Just want to check out where this number lands. I think it's somewhere in there. Just want to make sure. 1/16 is 0.0625. 9 divided by 16 is 0.5625. So 7/32. I'm pretty sure it's in the middle, somewhere in between those. Not the middle, but 7 divide that by 32, and it's 0.21. We'll call it 0.219. Which is greater than 0.0625, but less than 0.5625. So this one's somewhere in this range too. So let's do something else. So to be more accurate, increase the number of rectangles. So try to fill the area under that curve with as many rectangles as possible. Okay, so what we do to get the actual area under the curve is use a limit, and you take the number of rectangles and make them infinite. So we fill the area under the curve with infinitely many rectangles, and that's going to give us exactly what that area is. And as I mentioned before, we're mostly going to work with right-hand endpoints. So for this one, I'm going to jump straight to when you look at right hand, which is R sub n. And that area is exactly equal to the limit as n goes to infinity of the sum of all of those rectangles. Okay, so first of all, when we were approximating the area, which I'm going to slow down and, sorry, just like, I like this stuff and I'm excited, but when we approximate, you have an about sign, and it's the sum from I equals 1 to n of f of, we're going to call it x sub I star, because your x sub I could have been the left hand. Oh, actually I picked right hand. Okay, well, for right hand, it is x sub I. So x sub I times delta x. So this is like the height of the rectangle, the width of the rectangle, and then add the next rectangle, add the area of the next rectangle till you get to the end. The actual area is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. Cool. Okay. So the next part I want to write is to have it for any kind of endpoint that you use. So if you pick your right endpoint, your left endpoint, or a midpoint, we're going to call that, what does the book call it? My teacher called it a tag, but the book calls it a, it's nothing amazing. A sample point. Okay, cool. We're going to steal this. So again, both of these are specific to right-hand endpoints. In general. X sub I star be a sample point. So it can be the left hand, the right hand, the midpoint, or you can even pick something like more interesting. Okay, let's do the actual area is equal to the limit as n goes to infinity of the sum of all the rectangles. So the sum from I equals 1 to n. Yeah. Okay. The area of the rectangle is width times height. The height is f of x sub I star. Okay. The width is delta x. feel like that's good enough for today. So let's just label what's going on in the formula, and the next time I'll come back and do some examples. So again, x sub I star is a sample point from the ith interval. You put that point into your function to get the height of a rectangle. Let's do f of x sub I star is the height. Delta x is the width. Which makes this piece an area of a rectangle. All right, and then you add or sum all of the rectangles. And this means we're going to increase the number of rectangles. Okay, we'll practice using this tomorrow. So again, I might make quiz number 3 tomorrow. If not, we're just going to call it good with 2 quizzes. And